Quadratic Equations and Inequalities, College Algebra, Chapter 3, Section 3. Quadratic equations in one variable. An equation that can be written in the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a is not equal to 0, is called a quadratic equation in standard form. Now consider the zeros of this equation, the x-intercepts of the equation, and the solution set of the equation equal to 0. All three of these are essentially the same thing. You find all three by setting 2x squared plus 4x minus 16 equal to 0 and finding the values of x that make that statement true. Now, one way to solve a quadratic equation is to use factoring and to use the zero product property. This is a property we've used many times. All it says is that if a and b are complex numbers and a times b equals 0, then a must equal 0, or b must equal 0, or both. So for example, we're going to solve this. Now, why don't you give this a try, test your factoring skills, and then resume the recording to check your answer. The first thing we're going to do is we are going to divide everything by 2, because that will give us lower numbers to work with and make it easier. Then we're going to factor x squared plus 2x minus 8. We're going to factor it into x plus 4 times x minus 2, because 4 times negative 2 gives us negative 8, and 4 plus negative 2 gives us positive 2. That means that x plus 4 equals 0, or x minus 2 equals 0. Solving both of these, we get negative 4 or negative 2 or positive 2. So the solution set of the equation is negative 4, 2. Notice how it's written with the solution with the set brackets and a comma in between. Note that the zeros of this expression are also negative 4 and 2, and the x-intercepts are negative 4, 0 and 2, 0. Now, it's possible for the graph of a quadratic equation to have 1, 2, or no x-intercepts. In the case of 2 x-intercepts, the quadratic equation has 2 distinct solutions, one for each. In the case of 1 x-intercept, the quadratic equation has one solution, and we often call that a double zero. In the case of no x-intercepts, the quadratic equation is not touching the x-axis at all, and it has no real solutions, only imaginary ones. Here's an idea of what we mean using the graphs. We have a set for a positive parabola that opens up and one for a negative one that opens down. As you can see, when there are no x-intercepts, the graph does not touch the x-axis, and this is when we have imaginary solutions to the equation setting the parabola equal to 0. When we have one x-intercept, the parabola is touching the x-axis but not crossing it. And when we have two solutions or two x-intercepts, the graph is crossing the x-axis in two places. Now try solving this problem. Pause the recording and then resume it to check your answer. So x squared minus 6x plus 9 factors into x minus 3 squared equals 0, or x minus 3 times x minus 3, which means x minus 3 equals 0 or x minus 3 equals 0. We have the same thing. We have two factors, but they're identical. Gives us one number answer, which is 3. But because it's doing the job at two numbers, or two factors, that's why we often call it a double zero, or a double solution, or a double root. You can see on the table where 3 is the only number that gives you a y value of 0, and you can see by the graph that 3 is where the parabola itself touches the x-axis. We could solve quadratic equations in the form of x squared equals k as shown below. What we do is we subtract the k from both sides, so we have x squared minus k equals 0, and then we factor it into, it's a difference of two squares, so we have x minus the square root of k times x plus the square root of k equals 0. We set each of those equal to 0 and solve, and we get x equals k, or x equals negative square root of k. Now, you can solve it without going to all this trouble by just taking the square root, but as you'll note here, When you take the square root, you must have a positive and a negative solution, as you see here. And that brings us to the square root property. The square root property says that the solution set of x squared equals k is one of the following. If k is positive, greater than 0, then the solution is plus and minus the square root of k. If k equals 0, then the solution is simply 0. And if k is negative, then the solution is plus or minus I times the square root of the absolute value of k. And here's what it looks like graphically. In the first graph, we have where k is greater than 0, and you can see that it crosses the parabola in two spots. One will be the positive square root, one will be the negative. In the second graph, we have where k is 0, and of course it only touches in the one spot, and that is 0 itself. And then finally we have where k is negative or less than 0, and you can see that that line is actually below the parabola entirely, and there are no points of the parabola that touch that line, so our two solutions are imaginary. Now we're going to solve these two equations. Pause the recording, give it a try, and resume the recording to check your answer. Okay, so we take first problem, we divide it by 2, then we take the square root, and it is plus or minus I square root of 5. Part B, we divide by 2, then we take the square root, plus or minus square root of 7, and then add 1 to both sides. On the graphing calculator, you have the first one here. You can see we've got 2x squared, and the line negative 10 is way below it. The graph never touches it, which is why we have the two imaginary solutions. Notice that you cannot find these on the graph because they are imaginary. The graph is graphing real numbers. For part B, we can find the solutions on the graph. It will give us decimal approximations of the solutions. And you can see that the line is intersecting the parabola twice. You can use the intersection function to find those two approximate solutions. Now we're going to try solving by completing the square. You've already had a little experience with completing the square from section 2. This is actually a little easier since we don't have just a y or a p of x on the other side. We actually have a number. So this actually makes it a little less complicated. You're going to use the same principles, and why don't you pause the recording, give it a try, and then resume the recording to see how you did. Okay, for part A, the coefficient of x squared is 1, so we do not need to divide anything first. So we go ahead and start with step 2, which is to move the 2 that doesn't have an x away from the terms with the x's. So we'll subtract 2 from both sides. Next, we take the term in front of the x, the number in front of the x, the 4, and we're going to divide it by 2 and square it. So 4 over 2 is 2, and 2 squared is 4. So we add 4 to both sides. So now we have negative 2 plus 4 on the right, x squared minus 4x plus 4 on the left. The left-hand side factors into x minus 2 squared, and when we complete the square, this part will always factor into a binomial squared, and the right will combine like terms to get 2. And now we solve just like the previous problems. We take the square root of both sides, not forgetting our plus or minus, and then add 2. So our solution set is 2 plus or minus the square root of 2. The solution to part B is on the next slide. This time we do need to divide by 8. We'll notice that the 3 is already on the right, which is fine. That's where we were going to move it anyway, so we'll just leave it there, and we'll divide everything by 8. Now we have some fractions to deal with, but don't let those scare you. You can handle this. We're going to take the 1/4 that's in front of the x. We're going to divide it by 2. 1/4 divided by 2 is 1/8, and then we will square that and get 1 over 64, and we'll add that to both sides. The left-hand side will factor into x plus 1/8 squared, and the right side will combine to 25 over 64. We then take the square root of both sides. And 25 over 64 just happens to be a perfect square, and we get plus or minus 5/8. Then we subtract the 1/8. So we have x equals negative 1/8 plus or minus 5/8. We can actually solve both of these, do negative 1/8 plus 5/8, and negative 1/8 minus 5/8, and that gives us the solutions of negative 3/4 and 1/2. Now we're going to look at how the quadratic formula was derived. What they did to figure it out was they took ax squared plus bx plus c, and they first rewrote it into a times x minus h squared plus k, which we did in the last section. Then what we do is we actually solve it for x. So here's what that looks like. The first part should be pretty familiar. Of course, this time we have it equal to 0 instead of p of x, which makes it a little less messy. We divide everything by a, we subtract the c minus a from both sides, we take the term in front of x, the b over a, we divide by 2 and square it, that gives us b squared over 4a squared. We add that to both sides. The left-hand side factors into x plus b over 2a squared, and the right-hand side combines to b squared minus 4ac over 4a squared. Now it's starting to look a little bit like that quadratic formula we're familiar with. We're going to take the square root of both sides, so now we have x plus b over 2a equals plus or minus the square root of b squared minus 4ac over 4a squared. And then we're going to add, or actually, subtract the b over 2a from both sides. Notice they also took the square root of that denominator, 4a squared, the square root is 2a. So now we have negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. And since they have the common denominator, we can combine them into one fraction. So we have negative b plus or minus the square root of b squared minus 4ac over 2a. And here's that famous formula. And many of you learned it to the tune of Pop Goes the Weasel. Feel free to sing it, but not during a test. The expression under the radical is known as the discriminant, the b squared minus 4ac. And the discriminant can be helpful in telling us what kind of answers to expect. So if all they want to know is what type of answers, instead of going through the whole formula, all you need to do is b squared minus 4ac. If b squared minus 4ac is positive, then you're going to have two real solutions. If b squared minus 4ac gives you 0, well then that whole square root goes away and you're just left with negative b over 2a, which is one solution. And if b squared minus 4ac is negative, well then you have a negative under a square root, which means you have no real solutions. Instead, you have imaginary ones. Now, try using the quadratic formula on this. But first, you need to change it to standard form, which is ax squared plus bx plus c equals 0. Pause the recording to give it a try and resume the recording to check your answer. And there we go. When we change it to standard form, we get x squared minus 4x plus 2 equals 0. Then we put everything into the quadratic formula and solve, and we get 2 plus or minus the square root of 2. Let me remind you that for those of you who want to use your calculator to help you, whenever you go to square a negative number, you must put the number in parentheses with the square on the outside of the parentheses. Otherwise, it will not give you a correct answer. This is what the solution looks like graphically. Again, you can use the intersect here to find those two answers. However, it will only give you an approximation and not an accurate answer. It's still a good way to check your work. Now try solving this problem using the quadratic formula. Pause the recording to do it and resume the recording to check your answer. As we see from the title of the slide, this particular equation has no real solution. Our final solution is 1/4 plus I times the square root of 31 over 4. Graphically, we can understand this because the parabola itself does not cross the x-axis or even touch it. Okay, graphical interpretations for quadratic equations and inequalities. Here we have a parabola. It is crossing through the x-axis, and it is an upward opening parabola. Now the solution set of p of x, which is the parabola, equals 0. The solution set is a and b because those are the 2 points on the x-axis at which it crosses. The solution set for p of x is less than 0 is going to be the interval between a and b because between a and b, the graph dips below the x-axis. And the solution for p of x is greater than 0 is going to be negative infinity to a and b to infinity, because these are the intervals where the graph is above the x-axis. Now looking at a downward facing parabola, p of x equals 0 at a and b, same as before, but this time p of x is less than 0 from negative infinity to a and from b to infinity, because this is where the graph dips below the x-axis, and p of x is greater than 0 in between a and b, where the graph is above the x-axis. Okay, I'm just going to bring all of these up. This is the same idea, but this time instead of the parabola crossing the x-axis, it just touches it. So the solution set for p of x equals 0 is very simply a. The solution set for where p of x is less than 0 is the empty set, because it doesn't go below the x-axis. And then the solution set for where it is greater than 0 is negative infinity to a and a to infinity. For the downward facing parabola, very similar. P of x equals 0 at a. It's less than 0 from negative infinity to a and from a to positive infinity. And it's greater than 0, well, nowhere, so the answer for that part is the empty set. Now we have a graph that doesn't touch the x-axis at all, both upward and downward facing. P of x equals 0, well, nowhere, it doesn't touch. P of x is less than 0. Again, for the graph on the right, on the left, that's nowhere. It's completely above the x-axis. So the solution set for p of x is greater than 0 is going to be all real numbers. For the graph on the right, again, it doesn't equal 0, so that part's the empty set. It's always negative. It's below the x-axis, so it's negative infinity to positive infinity, or all real numbers. And then the solution set for where it's greater than 0 is the empty set, because it's never greater than 0. Now we're going to use this information to help us solve quadratic inequalities. The first thing you do with a quadratic inequality is you treat it like an equation and find out what the zeros are. Then you identify the intervals determined by the solutions of the equations. In other words, we're going to take a number line and break it up using the solutions that we found in step 1. Then we're going to test a value from each interval to determine which intervals form the solution set. What we're going to do is in each part that we've divided the number line into, we're going to pick a number and put it into the inequality and see if it works. If that one number does work, every number in that area will work. And if it doesn't, none of them will. So let's look at how that works with this particular problem. I'll walk you through it. The first thing we're going to do is we are going to treat it like it's an equation. When we do, we factor and get the solutions -3, 4. So what we're going to do with the -3 and 4 is we're going to make a little number line like this, and we're going to split it into 3 parts. One part goes from negative infinity to -3, then from -3 to 4, and then from 4 to infinity. We're using the two solutions that we got to the equation, -3 and 4, to help form the boundaries of these intervals. Notice that the boundaries themselves are drawn with a dashed line, and notice we're using parentheses in our interval notation because our original problem was less than, not less than or equal to. Now what we're going to do is we're going to pick a number in each interval and put it into the original inequality. So for interval A, I might pick -5, and I'll put it into the inequality, and I will get 25 plus 5 minus 12 is less than 0. Well, no, that's not true. It's actually greater than 0, so I know nothing in interval A will work. Then I'll pick a number for interval B, and since 0 is in there, I'm going to use 0. And I get 0 squared minus 0 minus 12 is less than 0. This does work, so interval B will work. And then I'll do the same thing for interval C, maybe picking the number 5. And when I do, I will find that it does not work. So I know that my answers must come from the interval in the middle, from between -3 and 4. Okay, this is a chart showing what I was just discussing on the previous slide. testing a number in each interval, and as we discovered, interval B works, so our answers are going to be between -3 and 4. This is really the best, most organized way of dealing with polynomial inequalities, and it's a good way of dealing with rational inequalities as well. So if you can get this technique down now, it's going to make things easier later on. Graphically, what are we talking about? Well, we can graph the polynomial, and we're looking for where it's greater than 0. So on the graph, less than 0, on the graph we see that it dips below the x-axis, again between -3 and +4. On the table, you can see we've got the zeros at -3 and 4, and in between we have negative values. Why don't you try solving this equation? Pause the recording to give it a try, resume the recording to check your answer. Let me remind you, you need to get everything in this equation on the left-hand side and have 0 on the right. So we get this in standard form, and then we factor, and we get two solutions, 3/2 and -4. So we're going to divide up our number line, as you can see there, into intervals, -∞ to -4, -4 to 3/2, and 3/2 to infinity. Since it's greater than or equal to, we're going to fill in those circles for -4 and 3/2, and when we actually write our answer, we're going to be using brackets for those. Then what we're going to do is we're going to test points in each interval, and that will help us get our answer. So here's where we're testing the points. In the first interval, the point satisfied the inequality, as it did in the third interval. The second did not. So our solution is going to be from -∞ to -4, and from 3/2 to infinity. And again, note that we did put brackets by the -4 and the 3/2 because they were included as a part of the answer. Now we're going to solve some formulas involving quadratics. What we're going to do is solve for one of the variables. So for our formula here, a equals pi d squared over 4, we're going to solve for d. And then for our other formula, rt squared minus st equals k, we're going to solve for t. Why don't you pause the recording and give this a try, and then resume the recording to check your answer. Okay, so for a, we need to isolate d. So we start moving things away. First we multiply by 4, then we divide by pi, and finally we take the square root, make it a plus or minus. Now what we've done next to that is, remember, we don't want to leave a square root in the denominator, so we need to do what's called rationalizing the denominator. And to do that, we multiply the top and bottom by the square root of pi. On the bottom, that just leaves us with pi, and then the pi on top goes in with the a. If you're wondering what happened to the 4, well, the square root of 4 is 2, so it came out front. So we have our final answer, plus or minus 2 times the square root of a pi over pi. And for part B, what we have to do for part B is actually use our quadratic formula. We're going to kind of treat t like it's our x. So t equals negative b plus or minus b squared minus 4ac over 2a. Our a is going to be r, our b is going to be negative s, and our c is going to be negative k. We just put all of those in there, and we end up with s plus or minus the square root of s squared plus 4rk over 2r. All right, the rest of these are some practice problems. You can try them, pause the recording to do that, and resume the recording to check your answer. And proceed this way till the end of the recording.